Bézout's identity in the integers states that if we have two integers, a and b, with the greatest common divisor equal to d, then there exists integers x and y such that ax plus by is equal to the greatest common divisor d. So let's prove this. We define a set S, which are all the linear combinations of a and b such that they are bigger than 0. So this set definitely has non-zero elements, and in particular has a minimum. Which we will call D. It will turn out to be the greatest common divisor, but that is what we will need to prove. So let's write A as a Euclidean division by D. So A is SD plus some rest, where the rest is between 0 and D. Then clearly, because we have the D is in S, we also have that R is in S, because this is a multiple of A, and this will give rise to a multiple of B, and moreover, R is positive. So we'll find that R is an element of S, except for the case where it is equal to 0. Now, that is the case because we had that D is the minimum of S and R is smaller than D. So therefore, R has to be 0. It can't be an S. Therefore, D divides A. Moreover, with the same type of argument, we find that D divides B. And therefore, D is a common divisor of A and B. But we needed to prove it is the greatest common divisor. So let's suppose that there is another divisor, C, of A and B. Then we have that D, which is AX plus BY, it has to be has to be C times some other integer. Let's call it U times X plus C times some other integer V times Y. And therefore, this is a multiple of C. So therefore, if we have a common divisor C of A and B, we also find that this common divisor necessarily divides D. Therefore, D is the greatest common divisor. Now, therefore, we have proven that the minimal element of this set S, which we call D, is the greatest common divisor, and therefore the greatest common divisor can indeed be written as AX plus BY. So this is the proof of Bézout's identity. A more advanced remark is that Bézout's identity holds in principal ideal domains, which are integral domains in which every two non-zero elements of a commutative ring multiply into a non-zero element so therefore an integral domain is a commutative ring in which every two non-zero elements multiply into a non-zero element, and moreover it is a principal ideal domain if every ideal can be generated by a single element. So examples of principal ideal domains are the integers, which we just saw Bézout's identity, as well as, for instance, every field, as well as, for instance, the ring of polynomials of one variable, and for instance, not the ring of polynomials of two variables. So if we have such a principal ideal domain, then if we define R to be the principal ideal domain, then we have an ideal which is R times A plus R times B. Then because it is principal ideal, and because this is an ideal, it can be generated by a single element, which we can call D, and therefore there is a linear combination of A and B, which is equal to D. So this is Bézout's identity. So Bézout's identity holds in principal ideal domains. There are rings which are not principal ideal domains in which the identity also holds. It's called Bézout domains. But they may be a little bit more esoteric. Now, because Bézout's identity holds in principal ideal domains, for instance, one can prove also Chinese remainder theorems and other theorems. Since Bézout's identity is a basis of a lot of calculations in arithmetic.